Okay, so today I'm going to start talking about natural language processing with H2O. I'm Megan Kirka. I'm a data scientist at H2O. Has anyone ever heard of natural language processing before, or how many? Yeah, okay. And anybody do anything with it, or just anybody actually used it, implemented it? Okay, so a few. All right, and then a couple other questions. Who here uses Python? Okay, and R? So a little bit more Python users, so we'll maybe do a Python demo today. And the last question, who's heard of H2O? Okay, great. Okay, so today we're going to be using H2O to solve a natural language processing problem. And I'm going to go over a little bit about how H2O works for those who aren't familiar with it. I'm also going to talk a little bit about natural language processing. Today we're going to specifically talk a little bit in depth about Word2Vec, which is on the H2O platform. So I'm going to time myself, 6:30, okay. So we're going to start out talking about the use case we're going to go over today. Am I not blocking? Okay. In this use case we're going to solve throughout this talk. Then we're going to do an H2O overview, as mentioned, talk about natural language processing, and then do a demo. So our use case. Today we're going to do the Amazon Fine Food Reviews dataset. Has anyone seen that on Kaggle? Yeah, so it's a Kaggle dataset. It consists of about 600,000 food reviews from Amazon. And it also has not just their reviews, but the review score, the rating. So it's from 1 to 5, if you're familiar with Amazon. And this is a dataset I'm using. We have some other variables, but we're going to focus mostly today on the score and the review that they left. So I want to be able to predict whether a food product has a good rating based on the review. So can I just take that text, that review text, and figure out if it was a positive or negative review? We don't have the positive or negative, we just have 1 to 5 stars. So today I'm going to say anyone with any product with a rating of 4 or above is good, anything less is bad. So it's just a simple problem. Can we just figure out, just from the text alone, whether or not this product was rated good, highly? Okay. So I'm going to start off with an H2O overview. H2O is an open source in-memory machine learning platform. It's parallelized and distributed algorithms, so all of the algorithms on the platform are distributed, written in distributed Java. We have different algorithms like random forest, GBM, GLM. We have some unsupervised learning algorithms like generalized low-rank modeling, autoencoders, k-means, and Word2Vec, which we'll focus on today. Okay. It's also easy to use and adopt because we have both R and Python APIs. I know it seems like almost all of the audience uses either one of those languages. So with H2O, you can use R or Python as a front end to connect to this H2O cluster running. The other advantage is big data. So H2O can run on Hadoop or Spark. Today we'll actually be running H2O on Hadoop for the demo. So this works if you have very large data that won't fit on your local computer. I don't know if anyone's ever run into memory issues if they're working with a really large data set. Yeah, but it becomes a hassle, and your R, Python will crash. It will take a really long time to run. And eventually what happens is you have to sample down your data. That works, but what if you're missing this important trend that you didn't know about? So we like to say no sampling at H2O, so you're able to run H2O on top of these big data environments, connect to H2O from R or Python, and run your model on that big data set. Okay, so here's just a picture of the H2O cluster. You can see, as I mentioned, that H2O will run on different Hadoop environments, and we ingest data from different sources like HDFS, SQL or NoSQL databases, local file system. Okay. And the data frame will be distributed across the H2O cluster. We'll talk more about that. So here's my H2O cluster. I've started it up somewhere. I'm the data scientist on the right. H2O cluster does not have to be running on my local computer, although it can be. And I want to do some machine learning. So I'm going to go into RStudio in this case. I have my RStudio script, and what I'm going to do is I'm going to connect to H2O using this h2o.init command, and we'll talk about that in the demo. And what that's going to do is it's going to connect me to this H2O cluster that may be running remotely. And as I mentioned, this H2O cluster can have multiple nodes or multiple compute engines. So in this case, I have a data set on this H2O cluster. It's been distributed across the nodes. That way, the whole data set doesn't have to fit into one node. Right? And from there, I can essentially use R to tell H2O what to do through a REST API call. So I'm still using R as the front end, but everything's happening in H2O. What feels like an R data frame or a Python data frame is actually an H2O frame that's not in my local computer. Only the head of it will be, or a pointer to it. So this makes it really easy to adopt because it's going to feel pretty much similar to how you usually use R or Python, but you're actually working with a huge data set that wouldn't necessarily fit on your local computer. Okay. So now I'm going to go into natural language processing. So what is NLP? NLP is a way essentially for computers to understand text and language. You can use natural language processing for things like sentiment analysis, topic identification. So there are techniques to just automatically give you keyword tags to text. You can also use it to improve supervised learning models, and that's what we're going to be focusing on today. How can we use natural language processing to help our existing supervised learning models? Okay. And one of the reasons why we would want to use natural language processing to improve supervised learning models is because the machines or computers don't understand language like humans do. So if they see two strings, dog and dogs, it views them as two completely different strings. It does not see their similarity at all. So you're missing out on all of that rich information you have because you know language. The computers will not get that. So if you ever have any data sets with any text or any text in general, it's going to be unused by the machine learning model. Does anyone ever have text in their data sets? So a lot of you do. And so if you leave it as is, it pretty much will go unused in a model. The model just does not know how to use it. And we're going to see this today with GBM. So there's a few different methods for natural language processing. The first I'm going to talk about is bag of words. Bag of words is essentially something like one-hot encoding of your words, of the text. So you're going to say, does the word exist in the text or not? Very simple. Probably going to end up with a really large data set, really wide data set if you have a lot of vocabulary. The second method is count-based. So this is a little bit more advanced on top of bag of words. What we're going to do is not only figure out does the word exist in the text, or in the review in this case, but how often does it exist in the review. So things like TF-IDF, that would be under a count-based method. TF-IDF stands for term frequency inverse document frequency. And what that does is it takes into account how often a term occurs in a text, and also how often that term occurs in all documents. And the reason for that is it's going to try to increase the magnitude of words that happen a lot in a certain text, but also decrease if it happens all the time across all documents. So things like the or these stop words should get lower weighting. And then the last method, which we're going to talk about today, is predictive. And this is where we're going to train models predicting a word or sentence from its neighbors. This is something like word-to-vec or recurrent neural network, if you're familiar with that. That's also under the predictive method. Okay. With the predictive method, with word-to-vec, what we're going to end up with, or with any of these methods essentially, we're going to end up taking a word, and instead of replacing that word with some vector, right? Some vector or some numbers that represent it. The reason why we want to do that is because computers understand numbers much more than they understand text or strings. So for example, with that dog, dogs, it doesn't see that it's any similarity, but maybe it's 2 and versus 2.01, it sees that that's close together. So it understands numbers much better, and we want to somehow take all our text and convert it to numbers. And those are the 3 different methods we can do for that. With word embeddings, we're going to get word embeddings from word-to-vec. And it's going to map our words to vectors, and it's going to do typically 100 to 1,000 length vectors. So we're going to, for each word, get this pretty long vector of numbers to represent it. Okay. So here I have two examples. We have organic, we have all natural. They're converted into a much smaller vector just for the purposes of the presentation, but you can see that now they're converted into numbers, a vector of numbers. Okay. And here's just a quick picture of the word embeddings. So not only do the word embeddings convert our text to numbers, which is helpful for machine learning, but you can also use it to understand the relationship between words. So if words are close together or have similar embeddings, that means they're similar words or synonyms. You can also use it to understand language like analogies, for example. Okay. So let's talk about what Word2Vec is actually doing and what the algorithm does. Okay. We're going to try to use a neural network to figure out the semantic meaning of words. The idea here is that words that have the same context have similar semantic meaning. So that means that if the words around this target word are the same, they probably mean the same thing. That's what we're going to go with. So basically, we're doing this to frame the problem as a supervised learning problem. Can we, given an input word, predict the neighboring words? Now, this is something we can solve. We can figure out how accurate we are at doing it. And the reason, again, as I mentioned, is if two words have similar context or similar surrounding words, we're going to consider them the same. And that's going to give us these word embeddings. So we have an example. It's even better than the organic all-natural brands I have tried. This is an Amazon review. And we're going to take this word all-natural, and we're going to try to predict organic and brands from that using this neural network. So in the input layer, we have all natural. The input layer is going to be kind of one-hot encoded of all the different vocabulary words we have. And we'll have a hidden layer, one hidden layer for Word2Vec. So this isn't deep learning. And in the output layer, we'll want to get back brands and organic. We want it to predict those neighboring words. Once we've trained that neural network, we don't really want to use a neural network to predict the target or the context around a target word. That's not important to us and it's not really helpful. What we actually want is this weight matrix from the hidden layer. And this weight matrix is going to be our word embeddings. And the idea here is that each word is going to get some smaller number of dimensions of a vector, depending on the number of neurons in my hidden layer. In this small picture, I have two neurons in my hidden layer. So I have two vectors with dimension 2. And the idea here is, again, as I mentioned, if the vectors are close together, then they're similar. Similar words that have the same context. In this example, we can kind of see that all natural and organic are kind of close together. So they kind of are similar, right, compared to, let's say, brands and tried. Okay, so here's a picture of the Amazon review, and I did Word2Vec on it. I did it with dimension 2, so this is much smaller than is recommended. You should do about 100 to 1,000. But I wanted to see what it looked like, and I wanted two-dimensional for plot purposes. So we can see I've highlighted a couple. Maybe it's a little small, but here's a sampling of different words in my Amazon reviews, and we can see that dogs, cat, dog, and treats are all kind of in the same area. And then up here we have words like chips, sweet, sugar, and chocolate. So you should see, just by looking at a graph, that it's starting to pick up the meaning of language. Right? It's starting to pick up from these Amazon reviews what's similar. Has anyone tried Word2Vec before? Okay, got some people. So with H2O's implementation of Word2Vec, we're using a skipgram. And we're using a hierarchical softmax to increase the speed. It's written in distributed Java, and you will get a Java representation of that Word2Vec model out. Another thing I want to add about Word2Vec, our Word2Vec algorithm, is it also intake a non-H2O Word2Vec algorithm. So for example, if you want to use Glove that's trained on all of the news articles, you can actually ingest that as an H2O Word2Vec model and still use H2O on it to do all your pre-processing. Okay, so now once I use this Word2Vec algorithm, I'm going to get for each word some numbers. It's this vector of numbers. So we have this, again, the same review. It's even better than the organic all-natural brands I've tried. So for each of those words in there, minus some stop words like the and of, we're going to get some word embeddings. But my goal of this talk is to try to predict whether or not a review is positive or negative. So for each review, I need one record, right? Because I'm trying to do a supervised learning problem. Each review should be one record, true or false, is it positive or not? So to do that, what I'm going to do is I'm actually going to take the word embeddings of all the words in the review, and I'm going to aggregate it using an average. So I'm going to have C1 and C2, the average of all the words in my review. Does anyone know of another way that we could consolidate these other than average? Okay. Well, we don't have to necessarily consolidate them. We could just kind of add them together. We could also do something like, depending on the frequency of each word, make them weighted differently, right? So if the word is more common, maybe it's weighted less. So there are different ways you can aggregate it. Right now, H2O supports the average aggregation. And this is going to give us one vector per review. And then before I finish up about natural language, or the intro to natural language processing, I want to mention that, does anyone know of maybe an advantage of word2vec over those count-based methods like TF-IDF? Yes?
The neighborhood context is much better in word2vec than the count.
Yes. Yeah, exactly. Now we have, since we're trying to predict the context around a target word, context or the location of the words is now important. So when you do a TF-IDF, it's simpler. You don't have to build a whole neural network, but you lose the whole location of where the words happened. So if someone says not good, that doesn't get picked up in TF-IDF at all. So typically it's found, Google did a study on this, found that word2vec typically has higher accuracy, higher semantic accuracy. Okay. Now our end goal, again, is going to be to predict positive or negative reviews. So this is just a supervised learning problem, and we're going to use word2vec as a pre-processing. Okay. We could technically, if we wanted to make a model, we could say, let's just do a rule-based model and say, okay, if the review contains tasty, great, yummy, it's a good review because it's food. If it says bad, hate, worst, it's going to be a bad review. This isn't optimal because there are probably a ton of words that we're missing that are positive or negative. And the other thing too is the context matters. So not good is going to be a bad review even though it had maybe, or not great would be a bad review even though it has great. So you're missing a lot of these subtle things, and there's so many different rules we could make that it would become so complex and crazy. Okay. So instead we're going to use a machine learning model. And the machine learning model hopefully will find out how to separate the distributions of good review versus bad review. Right? So somehow it's going to automatically figure out how to separate these records or these reviews.
Why isn't the full database a Gaussian curve? It seems to be having two different means there.
Oh, this is two different, so the green should be the good reviews and the blue should be the bad reviews. And hopefully we can see something like this where they have two clearly different distributions along some combination or one or more features.
But the combined view should be a standard Gaussian curve.
Yeah, but these are separate. Yeah. So if they were together, it would be standard. And now we're going to use a tree-based model to figure out, is the review good or bad? So we're going to use, in this case, a gradient boosting machine. Has anyone used gradient boosting machines? Okay, a couple. So these work really well with transactional data, which is what we have today. Okay, and I'm going to go into a demo. The last thing I want to mention is word2vec has a lot of different parameters. So how long the word embedding is, that's a parameter. How many epochs we train it for is a parameter. There are additional parameters. But it's really hard to figure out the best setting because it's not like we really want to predict the context of the target. We just really want to get good word embeddings. So there are a couple of different methods we can use to figure out if the model is good. But one thing we can always focus on is we have a clear target. Can we accurately predict if the review is good or bad? So we can always try to optimize the parameters so that we get the best supervised learning model. So think about it all in one pipeline. The word2vec is just the pre-processing. what parameters, how can we tune the parameters to get the best final model? Okay. So today is our demo. We're going to, again, predict whether the review is good or bad, and the first step we're going to have is to tokenize the reviews. So we're going to get all of these text reviews. We're going to import an H2O. I have the data set saved on HDFS, and we're going to import this data with text data, and I want to break up the reviews into separate words. We're going to use H2O for everything, and then we're going to filter words like the and if, all of these stop words. We're also going to filter any words that have like 2 characters, just kind of get rid of all these bad words. The next step, once we have our tokenized words, is we're going to train the word-to-vec model, which we were talking about, and then we're going to use the model to transform the reviews to vectors. And we're going to use H2O for this as well, using the H2O transform function. And then finally, we're going to train a supervised learning model to predict good rating. And we'll see how accurate we are. Okay. Any questions so far? Yes?
Will you train the word-to-vec model on this exact same corpus as the model you'll apply to in number 3? Meaning the reviews will be the same for number 2 and number 3?
Well, yes, I am, because it should be, well, the word-to-vec model doesn't know about whether or not the review is good. We're just using that as a corpus to learn context. So it shouldn't really have any data leakage. Yeah. Yes?
This goes back to your question earlier when you were talking about how there's like you can tune different parameters. For the how do you pick what size dimensional space to use? I know I feel like 100 is the default that H2O uses. But like, if you get up to 1,000, is that significantly better? Like, how do you decide?
So the question was, how do you decide the size of the word embedding? So typically it's 100, but what if 1,000 is better? That's really hard to tell, again, because the model is trying to predict the context, but we don't really care about the context prediction. What I would recommend doing is to write a script that will kind of do a grid search, where you have the word-to-vec, you transform, you build the model, and you get the accuracy of the model, and then you try another word-to-vec word embedding, and you should see then that there's some kind of local minima or maxima of accuracy. Yeah.
Can you take a word-to-vec model that you've trained elsewhere on a really large corpus and apply it to a small corpus?
You can, and that's actually one of the things that H2O allows. So there's a model, for example, called GLOVE that was trained on news articles. It's huge corpus, trained on a huge amount of data. You can actually use, what I would recommend is actually training a word-to-vec model specific to your data, and also training a model, and also importing a word-to-vec model that's been trained on a large amount of data, or some kind of predictive natural language processing model that's been trained on a large amount of data, and using both of them. The reason being is that sometimes you'll have language that's very specific. What the context is very specific to your data. If you have like legal data, maybe somehow the food reviews is specific to food and doesn't really translate to news data. But then also include this word-to-vec model that's been trained on a large corpus of data to see if you can get some additional insight. So use one, use both. Yeah.
I just follow up to this comment. And for the specific topic, the acronym and abbreviation is quite different. So.
Yeah, exactly. So I recommend trying both, but training on your data set too, just because it may be some specific, like food data, maybe it's somehow different. So let's start with the demo, and I'll take questions in a little bit. So I'm going to switch over to my Jupyter notebook. Is it big enough, everybody? Maybe I'll make it a little bigger. Okay. All right, so again, we're going to use that Amazon food reviews, and we're going to start by importing H2O. And then I'm going to write an H2O.init. And what that's going to do is it's going to connect me to a H2O cluster running on Hadoop. It's going to tell me the cluster's been up for 48 minutes. I got the cluster version, how many gigabytes of memory is free, and so on. And now I'm going to import the data from HDFS. So you can see my HDFS path. Let's import it. Okay. So I'm going to switch over to Flow. Flow is H2O's web-based UI. You can point and click through a whole machine learning workflow. And you'll notice that in the H2O init, you're going to get some IP port. You can go to that to see H2O Flow. And I can see all of my frames, for example. So even though I'm working in Python, I can still go to Flow and access everything that I'm doing. So we're going to see the reviews.hex. So I can see that I have about, 500,000 reviews. And we can see different things like the user ID, profile name, score, the summary, text. And let's take a look at the score. Okay. So here's a distribution of the score on the data set. So it looks like most of the time people rate a 5 on Amazon. So for whatever reason, maybe people don't like to review unless they really loved it. Most of the time, people liked what they got. Okay. All right. So we're going to start by adding that good review column, which I decided arbitrarily is 4 or 5. We could also treat this as a regression problem and try to predict the score. Let's take a look at the distribution of good review. So this is all happening on top of Hadoop. I'm just using Python on my local computer to tell H2O what to do. Might be a little slow depending on the internet. Okay. While that's running, I just want to talk through the next part. So we're going to be tokenizing words. I've defined first stop words. So these are all the words that I'm going to say are not to be included into my corpus. These are things like the, I, all, we. These are not helpful. They're commonly in the text, so we're just going to get rid of them.
But you took out not, so that means you're
Oops.
not.
That's a good point. So I shouldn't have taken out not. I didn't realize that. Okay. Thank you.
Is this
yes.
done manually?
You don't have to do this manually. I did the stop words manually, but there are multiple packages in R and Python that have stop words. That's probably better because I missed some and included some I shouldn't have. Okay, so here's the distribution of good review versus bad review. So it looks like we have about 4 times more likelihood of a good review than a bad review. So maybe this is different than Yelp. Okay. All right, so we're going to let that run. I have a function called tokenize. What this has is going to take in is sentences like my reviews and stop words. And what it's going to do is it's going to break up the sentences using this tokenize function, that's H2O function. By word, it's going to convert all of them to lowercase, and it's going to remove any word with character less than 2, or it's NA. And the last thing it's going to do is it's going to remove any words with a number in it. And then finally, it's going to remove any words that are in the stop word list. Okay. And from there, what I should get is a single H2O frame with all of the words in my corpus. Yeah?
So sentences is a whole review, correct?
Yeah, that's one review. Oh, it's the whole column of reviews. So it's really, you're just going to give it the column in your data set that you want to get tokenized. So in this case, I just return reviews hex and the text column. And here we can see the words. So bought several Vitality canned dog food products, found them good. So it's starting to give us the reviews. This is not just a unique word. It's going to be all of the words. So it's going to be as big as if you took all of the words in your reviews and lined them up into a vector. So if we take a look, let's see. Sorry. So this is pretty big, 28 million records. All the words in my reviews. From there, we're going to load a word-to-vec model. I'm not going to run it because it takes some time, but you can use H2O to run the word-to-vec model. And here's the functions I used just a little bit earlier. Now that I have the word-to-vec model, one of the things we talked a little bit about how do we know if the word-to-vec model is good. One of the things you can do is see how well your supervised learning model performs with these word embeddings. The other thing we have is something called find synonyms. And what this does is it will find synonyms for you for a specific word. And now synonyms in this case are words that have a small cosine distance in the word embeddings. So I'm going to try to do a sanity check and say, what are the synonyms for the word coffee? Let's see what the model found. So it's going to give me the first 5 words with the smallest cosine distance to the coffee word embedding. Okay, so we get the first 5. We get the first is cough, gets spelled wrong. Coffees, espresso, Starbucks, Starbucks. So these are just, yes?
Does it work for the abbreviations as well?
It should if they share the same context.
Oh, okay.
Yeah, and it looks like it caught some of the misspelled coffees, right? So maybe someone just forgot the last E or wrote coffees. And I guess that works. So it's finding plurals as well.
Can you try for, if that's
Yeah, go ahead.
Can you try for the word coffee instead of coffee? C-O-F-F-E.
Let's see. Good. Okay. Anyone want to throw out a couple more words we can try? Something that would be food related, so it would work.
Bread?
Bread. I hope there's bread here. Okay. Any others?
Tea.
Tea? Oolong. Okay. I tried dog before, so that worked, I think. Dogs, pop, treat, puppy. There's a lot of dog food reviews. So. No. Sorry, I should have prefaced that. Okay.
So those are all nouns. Something like an adjective like tasty.
Tasty? Okay, let's try tasty.
See what happens to that.
Sorry. Oh, that's good. Filling. So it's actually, and it's interesting to note that it's all finding adjectives. So when we were putting in nouns, I found all nouns. It's finding all adjectives, and that also makes sense because the context of an adjective will be similar to the context, of other adjectives. Okay. All right, so we'll keep going. Okay, so this is just running it. I ran it with the default in H2O. This is, I think, came out really good. I was surprised. But it had a pretty big corpus. So if you have the more data you have, the better it will get, just because it sees more instances of these words happening. If you have each word happening at one time, it's not going to learn anything. Yep.
How many sentences were there?
There was about 600,000 sentences, close to 600,000. Yep.
Did you carry out stemming before running this?
I didn't. That's a good point. And 600,000 reviews, not sentences. Most of the reviews are like paragraphs long, actually. People leave long reviews. Stemming. So someone asked about stemming. I didn't do any stemming here. So stemming is when you remove like the S or the ing and just give the root of the word. I didn't do that. And actually, Word2Vec should figure that out. And we saw that with coffee and coffees and dogs. So ideally, even though the stem may be different, the context will be the same, and it will pick up that there's synonyms. Yep.
For the synonym, how do you compare the accuracy with the WordNet synonym accuracy?
How do we check that the synonyms are accurate?
How do you compare the accuracy here with the WordNet? WordNet is a natural language.
Oh, I'm not sure. I think WordNet. I'm not sure how. I think Google has a comparison though. Yep.
Can you leave in the stop words before training the Word2Vec and then get rid of them before you do the averaging? Because in Jensen, you usually keep in your stop words before.
Yeah, you can do that. I don't know if there would be an easy way to remove them after for the averaging, but you can definitely leave your stop words in. Okay.
Can you try 2 words together? Is that possible?
Oh, like a phrase? No. It would, well, depends on how you tokenize. So with how I tokenized it, my function I defined as each word. If you want to do it some way different, you're definitely welcome to do it. And
Try stale.
stale?
Stale. Stale
Okay.
coffee.
Let's see. Ooh, that's pretty good. Right? Okay, so he has some bad reviews. Okay, so here is the transform function. So this is what I'm actually using. I'm going to take all the words, and I'm going to use my Word2Vec model to aggregate the words per review. So it's really easy to do. I don't need to write any complex function. I just need to write transform. And the aggregate method is going to be average. So it's going to take all the word embeddings for the words in a review. It's going to average them together, and I'm going to get one record per review. That's going to be, in this case, 100 columns. Okay. So if we take a look, let's take a look. So here are the word embeddings. For each review, I have one record. It's going to be 100 columns, and it's the average of the words in that review. Okay. All right. Yeah.
It's a straight average. I mean, like an arithmetic average.
Yeah, it's an arithmetic average. We may want to do something like a weighted average. You know, maybe like frequent words are weighted less. We could try that. But right now, just average. Yep.
Maybe my intuition is wrong, but it just feels like you might be like losing data.
Definitely, definitely. The other thing we could do instead of averaging is we could keep all of the word embeddings and just like put them next to each other, but that will become a really wide data set. Because you'll think like if every review has 100 words in it and there's 100 columns for each word embedding. Yeah. Okay, but I agree. So we're going to train a GBM model now to try to predict good or bad review. We're only going to use these average word embeddings. So here I'm defining the GBM. I'm going to say my Y, my response column, is good review. And I'm going to try to train the data on a split frame. Did I split the data? I split the data into training and testing with this function here. And I'm going to try to build a model. Okay, so we're going to go over to flow while this builds. And I'm going to click on models, list all models. And I'm going to see my GBM model here. And I can actually watch as this model builds. So here we can see the scoring history, the log loss. As we build more trees, we should see that this goes down. Right? So the orange is going to be the validation data, and the blue will be the training data. If we see that the orange or the validation data's log loss starts to plateau, that means that we're overfitting. It just finished. I just ran it with the default settings for 50 trees, and it looks like it's not overfitting. It looks like we could even build more trees. Just a little bit of background about GBM. Each tree is built on the error of the previous tree. So it's like random forest in that you're doing a bunch of decision trees. But rather than just having each tree be completely independent of the other ones, each tree now is trying to fix the error of the previous tree. So it's always trying to fix itself. And these do very well with transactional data, GBMs.
What do you mean by transactional?
Like not images, not audio, just like records, regular data, anything in Excel. Okay. So here we can see the ROC curve for my training data. We can see the AUC, the area under the curve. For the training data is 0.89. Okay. And now we can look at the validation data. We get the same ROC curve on my data set, my test data set. Now the test data set, the model has never seen before. So we're just using the training data to train the GBM models and figure out where to split. And then we see how well does the model perform on the testing data. And the reason for that is we want to make sure the model still does well on a holdout data set. Now we can see here that the AUC is a little bit smaller, it's 0.88. Any idea why the AUC would be worse for the validation data than it is for the training data?
I don't know how you could apply it to the validation data. I mean, that's the way the AUC would be built, right? So you build it on the training data which you scored
Yeah.
out, and then you test it on this. So you can only quote this score, not that score.
Well, we would probably only talk about the validation one because training, you could build a really complex model and get 100% accuracy. So for example, I want to predict age and I know everyone's social security number. I could get 100% accuracy on age, and then when I get a new person, I'll have no idea what their age is. So that's a really overfitting model. In this case, we really want to make sure that it does still well on the validation data, and it looks like it does comparable, right? So 0.89, a little bit worse on the validation data, which is to be expected, but it's not that much worse. We can actually play around with this ROC curve and click on a point and get the accuracy for this point, the precision recall, and the confusion matrix. When I click on a point, I'm actually choosing a threshold, and I'm saying if any record or any review with the probability of being good is greater than 78%, mark it as good. Anything else, mark it as bad. How many times am I right when I do that? How many times am I wrong? So we can pick different points and see how well we do. We can also say we want to maximize some criteria. So we may want to say we want to maximize our accuracy. And if that's the case, this would be our threshold, and this would be our accuracy, 85%. So in this case, we have 85% accuracy in predicting whether or not a review is good or bad, based on just the text alone. We don't know about the product, we don't know about the customer who reviewed it, nothing. Okay. And you can see that we have a pretty good, pretty low error in predicting yes, they're good. We have a higher error for predicting no, they're not good. Anyone have an idea about why we would have a higher error for predicting the bad reviews? It's unbalanced data. So in unbalanced data, almost always it will do better on the popular class and worse on the unpopular class. Any way we can fix that? Yes, what do you say? Smote's one way. Smote will actually create new records of the minority class. One other way we could do is we could weight the classes differently. So maybe we say that it's twice as important for the GBM to get the bad review right than it is to get the good review right. And we can do that with H2O. So if we go to my model GBM, here we can see my parameters. You can also build the same GBM in H2O flow. And we do have an option for a weight column. So if you want to add weight to that minority class, you can do that. Okay. The last thing I want to mention is we have a variable importance. So here we can see which variables are the most important in predicting whether or not somebody defaulted. So in this case, C89 is the most important. Okay. We don't really know what that means. We can do some examinations to see which records or which words have a high C89 value, which ones have a low C89 value, and we'll talk about that a little bit more. There's some gains and list tables, and then we also have the POJO. So this is the Java representation of the model we just built, completely independent of H2O. We go down, I'm just going to go down a little bit. It's actually just Java code, it's just if-else statements. So this is really low-level Java. You can see it's just kind of memorizing the tree, the path the tree took. So in this case, if C89 is less than 0.39 and C81 is less than this and so on, you're going to predict this. So this can be used for maybe now if I want to build some product that will automatically tell me good or bad review. I can use this in my production. Okay. So let's see. We had the GBM model, and we saw that C89 was the most important. Something that's specific with GBMs is that it's a nonlinear model. So you don't know exactly how the variable affects the predictions. You just know that it has a large impact. With linear models, you're going to get a coefficient for each of your variables, right? So you're going to get -5 or something. You're going to know exactly how they affect your prediction. With nonlinear models, we're a little bit more in the dark. And the reason being is there's no simple relationship between the variable and the prediction. It could be that when C89 is high, it's a high likelihood of being a good review. And then when it's really low, again, it has a high likelihood of being a good review. So let's take a look and see what the relationship is. Sorry. We're going to use partial dependency plot. Anyone used them before? No? Okay. Yeah? Someone? Okay. And what this is going to do is it's going to, let's get our frame. Oops. I'm going to do it on the, sorry. Let's see. One second. All right. I can't remember where it was. All right. Maybe I'll do that in a second. But before I do that, I want to talk about kind of pipelining this. So we have a model that predicts whether or not someone had a left or good or a bad review. But now I'm going to write a function called predict. What that's going to do is it's going to tokenize the words in my frame, whatever frame I give it. And it's going to transform it using my word-to-vec model, so I get the word embeddings. And then it's going to predict using my GBM model. So let's try and see what comes up when I try to predict. Seriously, this product was as tasteless as they come. And then great taffy at a great price. Yummy taffy, delivery was quick. This person loved their taffy. So we're going to see what the model thinks. Okay. Let's get the partial dependency model. And we said it was C89. Okay. So that's computing the partial dependency plot, and let that run. And in the meantime, we're doing the prediction on seriously this product was good. It's parsed the data, it did the word embeddings, and then it did the GBM prediction. So in this case, it said no. So for the product that it was tasteless, it said it had 9% likelihood of being a good product. That doesn't make our threshold, so it's a no. And this kind of makes sense because we looked up some words like stale, and it looked like it was understanding bad words about food. The other one, the great taffy, it's still running. Okay, sorry.
How do I reinterpret that, Josh?
Yeah.
Yes is 9%.
So it has a 9% likelihood of being yes, 9.07, so then about a 90% likelihood of no. And the threshold automatically is chosen as the one that maximizes the F1 metric. In that case, I'm not sure what it is, but it's higher than 9%, so it says that this is no. It's going to be predict no. It's not a good review, excuse me. For our taffy, it says that we had a 96% likelihood of being a good review. This was the tasty taffy, yummy, delicious, delivery was quick. So the model gets it right both times. In this case, let me go back to, and we finished our partial dependency plot. So I did build a partial dependency plot on that C89 feature, which was the most important feature in our model. And I want to understand how it affects the predictions. So what this is showing me is what would the prediction be if I changed everybody's C89 value to 0? What about if I change it to 0.1? What about 0.2? I'm going to take the average of all of the frames predictions if I change the C89 value. So it looks like here, people with a low C89 value have a high likelihood of being a good review. So we could dig into C89 and figure out what does it represent? Does it mean, do words with high C89 value, are they words like tasty and good and yummy, things like that? Okay.
Which would then be the words you'd use in your ads.
Exactly, yeah. So you could take that information and use that for even additional things, like maybe you want to advertise with these words. It's a good idea. Okay. I'm just going to go back. Yep, I think that's the end of the demo and the end of the talk. So it's I guess now will be time for questions. Yep.
So
Sorry.
I don't know how dumb this may sound. What exactly?
Sorry, no, go on.
Okay. So, what exactly is the purpose of H2O? Like, it's to train the model, or it's to take care of post tagging, stemming, or like, is it a complete thing, or is it just?
I would say probably the most common use would be to train this final supervised learning model, but you saw that it did kind of do that stemming for us. So you don't need to just use it for building models. You can also use it to take that word embedding and then use that for finding synonyms, finding maybe doing stemming that way. Definitely. Sorry, yeah?
So right now you have two classes, good and bad. What if you classify 5 classes, reading from 1 to 5? Would the result be good?
I did that, and I had a mean absolute error of 0.7. So it was basically like less than 1 off, which is good typically. I think it did pretty good. That's a harder problem because now we have to get more specific. Good and bad was kind of making it easy for the model. Anything with multinomial would be the hardest. So if we really treat it as 5 different categories, not numbers, that would be probably the hardest for the model to get. Yep.
It's very interesting the way the dependency plot showed C89 to be kind of like a major factor, right, in that
Yeah.
relation. I'm wondering if C89 was used out of context, like in a sarcasm or some other non-standard way of representation, right? So would a doc-to-vec be a much better model in this case, where you're now vectorizing the entire review versus tokenizing it, which is kind of like a word-to-vec, but
Yeah.
right?
Maybe definitely, because when we aggregate it, it's going to lose a lot of that information, the sarcasm.
Yeah, and
Yeah.
it's hard when you're looking at slang, like this coffee is bad, meaning it's good.
I don't know if so. No, I know what you mean, but I think the Amazon reviews are pretty. I didn't see that much slang,
Okay. That'd be nice to pull that out.
but it would be interesting, yeah.
But if you increase the window of the words that it takes in context, can you improve on that?
So that's another parameter that we can play around with, the window size. So what does context mean? Does it mean the word right before and right after? Or does it mean 2 words or 5 words? Again, that's hard to gauge. I would say try different values and see how your model improves or doesn't improve. Yeah, sorry.
When you ran the prediction on those 2 phrases, it seemed a little slow.
Yeah.
What would be the cause? Is it the word to vec slowing it down?
I'm not sure if it was, I was doing it on a remote machine, so I don't know if it could have been the connection. Maybe I just need more power for my H2O cluster.
Because GBM should be pretty fast.
The prediction of the GBM, I think, wasn't the slow part. I think it was the taking the words and tokenizing them and then getting the word embeddings from them and aggregating it. So there was actually a bunch of different steps going on there. It had to tokenize, look up the word embeddings, aggregate them, and then once it had that, it would do the predict on the GBM. I think the GBM prediction should have been pretty quick. Yeah.
All right, Megan.
Could you take the whole good data set and run it again to see what is very good versus maybe average? Instead of bad and good?
Yeah, we could definitely, that would be a multinomial problem. So we could say good, okay, bad. Definitely.
No, just take the good data set.
Oh, yeah, we could definitely do that as well. So the question was, could we take just the good and separate it into good and average? Yes, we can do a filtering in H2O, so maybe anything greater than 3, and then now label it good or average. That's all possible in H2O. Yeah.
Okay,
Sorry.
a few questions.
Yeah. Oh, okay. So we have some questions on the screen. How do you determine how large a vector space to use, 100 versus 1,000? So I think we discussed that a little bit, but one way was kind of checking the synonyms. So sanity check, does the synonyms check out right? That's a good way to do it. The other way is to see how well your final supervised learning model performs. And I always think, what's your goal with this project? Right? My goal was really just to figure out good, bad reviews. So if you would kind of need to define your goal and figure out how to do all your pre-processing that improves that final goal. Same thing with any feature engineering, parameter tuning. You're going to just figure out, does it improve my accuracy of that final supervised learning model? The second question, which pre-trained word vector library did you use in your word2vec algorithm implementation? Okay, so this is an H2O implementation of word2vec. It's written in distributed Java by the H2O team. However, as I mentioned, you can import existing word2vec models into H2O, like glove, for example. Okay. Does H2O support any standard way of importing custom NLP models with tune parameter and epoch settings, given that PML standard supports for text is limited? Does that glove answer cover that question? I don't know who asked it, but is it like a custom algorithm or a custom model?
Yeah, any of the models that we build in R,
Yeah?
if we were to import it, one way would be PMML, but for text, it's kind of a standard settings.
I don't think you can import PMML, but we do have an example of importing a non-H2O model into H2O. So I can try to, if you come over at the end, I'll just share it with you. Okay. Is there any advantage of predicting from the speech over star rating to determine good or bad review? The only advantage is that it makes the problem simpler. It's also easier to understand how well the model performs because we typically understand accuracy very well. Something like the root mean squared error is a little bit more vague. So for the purpose of the demo, I did a binomial problem, but you can definitely do regression instead. And that would be maybe more precise. Because maybe a 3 versus a 4 rating, it's kind of not that different. So it could be better to do ratings instead. How different, so in the NLTK, are you talking about the NLTK to get stop words? Or if we were to use, does NLTK have word to vec? I don't know who asked the question, I'm sorry. So I know NLTK has stop words. If we use the NLTK stop words, maybe we would have had a better result because probably I missed a lot of those stop words when I wrote them out manually. Okay.
Any more questions?
Thank you. Thanks, everybody.